Hello, everyone. My name is Smith Shah, and along with me, I have my colleague Sayan Chakraborty, and we are both from Zillow. Today, we are super excited to share the topic scaling AutoML-driven anomaly detection with Luminaire. Detecting anomalies in your data as early as possible has always been the most important thing for any organization, and so is it for Zillow. Now, with increasing in number of key metrics that the company monitors, it has become really important to scale and make it an AutoML-driven solution. So one important note before we go further, if you have any questions, please make sure to use the session's Q&A feature. So let's begin. So as I said, we are both from Zillow, but within Zillow, we are part of the data governance platform team. Our team focuses on two primary components, which is platforms and processes around data governance. There are four main pillars for our team focuses on, which is data discovery, quality, security, and privacy. Along with me, I have my colleague Sayan Chakraborty, who is a senior applied scientist at Zillow, and myself, Smith Shah, working as a senior software development engineer in the big data domain. So our agenda for today is going to be, we're just going to talk about what is Zillow, if in case not many of you might not know. We are going to talk about why monitor data quality, various data quality challenges, the main topic, which is Luminaire and scaling, and we are going to wrap it up with some key takeaways. Okay, so let's begin. So let me first talk about Zillow. Zillow is an online real estate company, which is reimagining real estate to make it easier to unlock life's next chapter. Now, this is possible by offering customers an on-demand experience for selling, buying, renting, and financing with transparency and nearly seamless end-to-end services. Now, this is possible with different brands and businesses that are available under Zillow Group's umbrella, and that is what you can see on the top right section. We are right now the most viewed real estate website in the United States. And our Q4 2020 stats also shows the same. We had around 201 million average monthly users, 2.2 billion visits, and we have more than 135 million homes which are available on our website. So let's go into the next topic, which is why we should monitor data quality and why it is also important for Zillow. So as I said, Zillow is all about homes, and we are a real estate company. So let's take an example of this home details page for a specific home. Over here, you can see information related to bedrooms, bathrooms, square feet, address, all the images that we show. So you can see like data is very important to us, and that's bad data will lead to bad decisions and broken customer experiences. Along with that, we show information related to Zestimate, which is used to estimate the prices of each home based on various factors. We have this service called Zillow Offers, which helps an easy and hassle-free service for customers to sell or buy a home. Along with that, we have our Zillow Premier Agent services, which helps customers to connect to agents. And we have our economic research team, which publishes a lot of various market research analysis on our website and various other teams. Now, apart from the customer-facing services, we also have a lot of ML and AI-based services, which are either surfaced internally or externally, for example, Zestimate, recommendations, and everything. So we also want to make sure they are also performing reliably, and also the data which is used by those systems are also of high quality. Overall, it is very important for us to monitor data quality, and as assumed, it will be similar even in your organization. So then let's talk about what does anomaly means and why is it important. So let's take this example over here. Over in this time series chart, the y-axis is the observed values, the x-axis is the time series, and over here you see there is a certain spike. So an anomaly can be any data instance or a behavior significantly different from its regular pattern, which is pretty quite obvious. And why is it important? Because this kind of anomalies are inevitable. Anomalies are going to happen within your data, and you just want to make sure you figure that out or detect them. They are going to be complex. The reason is because your time series trend might have different seasonalities. There might be certain spikes or drops, or there might be changes in your trend. And all this is time sensitive because you want to catch the anomalies as early as possible in order to avoid downstream longer effects. Overall, it is very important to catch anomalies. So, and it also helps you to make better business decisions. So let's talk about various ways to monitor data quality. There are two main ways, which is first is the rule-based checks. Now, rule-based checks are very easy, where you might have various domain experts who are either generating or utilizing these data sets, and they have various sets of predefined rules or thresholds that they can set on this data. Now, for example, percentage of null data should be less than 2% per day for a given metric, and so on and so forth. They are less complicated to set up, and they are easy to interpret. And they work well when the properties of the data are simple and remain stationary over time. But what happens when some of your metrics you cannot apply rule-based checks on them? That's where the second part comes up, which is the machine learning-based data quality checks. Now, these checks are rules that are set through mathematical modelings. For example, models that understands the historical data and figures out the predictions or doing an anomaly detection on a future value. They work really well when properties of the data are complex or they changes over time, as the example I showed before. And they are more hands-off approach because you don't need to have much domain expertise. They just understand based on the historical trends or any other external parameters that you supply to it. Okay, so let's go on to the various data quality challenges, and I'm going to hand it over to my colleague, Sayan. Thank you.
Hey, thanks, Smith, for such a great introduction. Hi, guys. My name is Sayan, and I'll be talking about the different challenges of data quality monitoring. So first of all, data quality is a highly contextual problem. And in general, the context depends on the use case. For example, when you're monitoring user traffic over a narrower time window to understand the status of a website, that is one context, versus you can observe the same user traffic over a longer term time window when you're considering to understand the business growth or something similar. Also, data quality depends on the reference time frame. It changes a lot when you observe that over a shorter time window versus a longer time window. One good example is COVID. If you take a time frame from COVID, that might not look anomalous unless you're taking a reference time frame from past few years. Also, temporal pattern depend on lots of internal and external factors. So all the external factors need to be considered into the model in order for the model to understand whether a spike is anomalous or non-anomalous. One example can be a user traffic which spikes up, and that might be related to some product launch or a marketing campaign, and that might not be known to the model, and it would be flagged as anomalies. So let's talk about the challenges that we face due to the contextual problem I mentioned before. So all of this context from the previous slide creates the challenges for the modeling part, because there is no one model that can fit all the problems that I mentioned before. So there are different time series with different patterns, and you need different models for that. Also, definition of anomalies changes for different level of aggregation. For example, you might want to observe user traffic per second versus you might want to observe user traffic per day. And the pattern of anomaly change a lot in terms of the modeling context. And all of this contextual information and the corresponding technicalities require strong expertise, not only from the machine learning side, but also needs lots of domain experience. For example, you might need to know economics, business, or from software perspective, you need to understand data engineering in order to add anomaly detection for your data. And that kind of creates a huge friction point for PMs or data engineers who want to monitor their data and get high quality data. And another obvious reason is the scalability, and you want to have a system that is scalable to support large amount of data across teams. So this all things kind of created the motivation to build a central data quality platform to not only democratize the access of high quality data across teams, but also create a data quality standard in the company. So before diving deeper into the system that we build to do anomaly detection at our company, let's create a set of wish lists that we want to have as a requirement for our system. So first of all, As I mentioned, all the context and the scenarios the data can come from, I mentioned before. So the system should be able to catch any data irregularities over different kind of context. Then the system should be able to scale to support wide ranges of data from different teams, because there are different services that are processing like enormous amount of data every day. Then the system should require minimal configuration and should be able to handle all the complexities related to anomaly classification automatically. And finally, last but not the least, the system should require minimal maintenance over time. This is very important for time-dependent data and keeping the scalability in mind, and also will reduce intervention from the developers, which in turn improve the resource allocation for the company. So before we started building this platform, we actually looked for several existing solutions, and we couldn't find anything that meets all these four criteria. And that kind of created the motivation of building our own internal anomaly detection platform that we called Luminaire. So let's dive deeper into Luminaire. So let's understand what is Luminaire. So Luminaire is Zillow's internal anomaly detection platform that performs automatic anomaly detection and also is self-aware. We recently open sourced Luminaire modeling library, so which also we call Luminaire, but that only contains the models. In the next few slides, I'll be going over some examples of like how we built our system around this modeling library to automate the data quality needs within our company. So before diving deeper, dive deeper into Luminaire, let's understand some key features. So Luminaire is a time series anomaly detection platform that is enabled, that is capable of doing data profiling and pre-processing. It is integrated with different kind of models for different scenarios that I mentioned before. It is capable of running for both batch and streaming use cases. It has an AutoML layer built in to optimize all the configurations. And finally, it is not only proven to work well in different contexts, but also has been shown to outperform many existing solutions in different use cases. You can use the GitHub link and tutorials from the slides to go over to go deeper into like how Luminaire works and how you can use Luminaire for your system. Another good resource to understand Luminaire's deeper mechanism is the scientific paper that we published in the IEEE Big Data Conference last year. So let's get a high-level understanding of the Luminaire component. So at a high level, Luminaire has two main components. One is the training component, and another is the scoring component. So the training component consists of different subcomponents that can be called as layer. So at the very bottom, we have the data profiling or pre-processing layer, followed by the modeling layer that can be called for both batch and streaming use cases. And finally, we have the AutoML layer that optimizes the configuration of the bottom two layers. And then we have the scoring component that pulls the right model based on the correct identifier for a given time series and score a given time point or a time window. So I'll be going over a couple of code examples in the next few slides, and all the code examples are taken from our GitHub page. So you can always go back and revisit them in future for your reference. So first is the data profiling and pre-processing layer. This layer prepares the data before sending it for training. This layer performs all the transformation needed for anomaly detection, also includes imputation if the data consists any missing data. Also, this layer performs some data profiling, such as like if the time series has observed a change point in the past, or if there is a trend change, which is an integral part, which is integral information about the time series, and also can be leveraged at the time of training. So you can see like you can use a data exploration class from Luminaire. You can pass your configuration and call the profiling function and get all the profiling information along with the pre-processed data. Next is the modeling layer. The modeling layer consists of different type of model that supports different scenario. And also modeling layer is capable of running the model for both batch and streaming use cases. So in this example, we have the Luminaire structural model, which can understand the time series pattern based on the historical structure of the time series. So you can use the Luminaire lat structural model class and pass your hyperparameter and call the training function to do the training. Similarly, for streaming data use cases, Luminaire has a window density model, and you can use a window density model class and pass your time series, and it will run the training based on the configuration you specified. Finally, at the top of the training component, we have the AutoML layer, and that AutoML layer consists of like optimization algorithm, which can optimize all the data transformation step, data truncation step, the selection of the models, and also the model parameter that I mentioned in the previous slides. So you can use the Luminaire hyperparameter configuration, hyperparameter optimization class, and you can get the best configuration for a given time series. So at the scoring time, Luminaire pulls the a model object, and you can run the scoring function in order to score a given time point for batch scenario. So in this example, you can see like we have scored for 2026-8, and we have passed a data point, and it has generated lots of information such as anomaly probabilities, confidence level, predictions, and so on. Also, in the streaming scenario, instead of scoring a time point, you can score a window. So you can have a trained model for streaming use case and pass a time window in the scoring function. You can get the time window score, and this will give you informations like anomaly probabilities and so on. So with that, I'll pass it over to Smith again, and he will walk you through how we have achieved scaling our system to support wide ranges of data set across the company. And also he will walk you through how we have achieved the self-awareness within our platform. Thank you.
Okay, so let me then go over through the various scaling challenges that Sayan mentioned and how we are able to solve that. So this is the architecture that we are using within Zillow, and you can see how we are also leveraging our open source Luminaire package, and also something that you can also incorporate and build some systems around it. So let me break this down into 4 sections. And also for everyone, there is also a link at the bottom that you can use to refer to our blogs, which also has more details around it. Okay, so let me then go to the very first part of this architecture, which is the training data that we need to use to generate the trained models. So in this case, we are going to prepare our input data set. Usually what happens is we don't want to monitor only one matrix at a time. There is always going to be cases where you want to monitor like K amount of matrix, and that's where like all the scaling and everything comes into place. So what we want to do is we want to divide this whole training data sets into K time series. And we want to give that as an input to your training. Now, each of this time series, like your K time series, needs to be assigned a unique identifier. This unique identifier becomes the key component when we store all the information related to the model and the scoring results in our system and map them out together. So once you are prepared how to distribute your training data, let's go through the training process. Now, this is our training process, which is our actual AutoML part. Now, think about this process. This process takes place for all of your K matrix. So each of your matrix is going to go through this entire cycle. And that is something we want to also distribute it. Okay, so let's take the example of our time series 1 in this case. Now, the very first time when we load our historical data for time series 1, since it's the very first time, we don't have any historical information about all the scoring or the models for that specific time series. So in this case, what we do is we first go through our configuration optimization, for which we use our open source package and what Sayan also explained. Using that configuration optimization, we figure out what is the right model to use from our suite of models that we provide, and also relevant parameters that needs to be passed for that model. Now, all this information is later on stored in our config storage. Now, this training data for time series 1 also goes through our data pre-preparation process. And in this also, we are using our open source package. which is responsible for cleaning the data. So there might be some kind of trend shifts happening in your historical data. So you want to exclude that from your training process and other benefits that it comes with. Now, what we do is like we use this clean data and the configuration that we have stored in our database altogether do our training process. Now, this training process later on generates a model, which is a trained model, and that is something that we store in our model storage. Now, we also associate the unique identifier for that time series one. Now, at the end of this process, what will happen is we are storing K models within our database. Okay, along with during our data pre-preparation, we are also storing some data profile information in our database as well. So it's pretty obvious. After this training process, we are going to talk about our scoring process. So during this time, what happens is like you want to score some newer data points that are coming in for this data set. So you're also going to do a similar process like splitting those data into K time series or K data points if you're only scoring one data point or if you're scoring n future data points. Now, what happens during the scoring process is it identifies the specific time series and figures out what is the unique identifier associated with that. It will pull that relevant model, which is stored in our database, and it will be most recent model at that time. And it will do the scoring process. And the scoring results are then stored into our result storage database. We also have our alerting services on top of the scored results because we, as Sayan mentioned, we are also outputting various anomaly probabilities. So you can set up the sensitivities based on that and alert your stakeholders accordingly. Now over here, there is this one important pipeline that is going, which is that information from the scoring related to the scoring performance matrix is later on stored in our log storage database. Now this becomes very important because one of the key problems that Sayan mentioned was having a very minimal maintenance of our models. And this is the one that helps us drive that. So let's see how that looks like. So the final step is using that log storage, which is our scoring performance matrix. And the next time when you go through the training process again, because this is time series data and your patterns keeps on changing. So you want to make sure you keep on retraining your data based on newer historical data as well. So what happens, let's take the example of time series one again. Now at this time, when the data comes in, it will look at the log storage and figure out if any of our performance metrics were not meeting our specific benchmarks. If the answer is yes, then we will again go through the whole configuration optimization process, store the new configurations in our database. We will definitely again, and if the answer is no, we'll just do the whole data pre-preparation based on the newer data. We'll clean them, and then during the training, we'll either use the past configuration storage, configuration information which is stored in our database, or we'll use the newer one and generate the model object. So this way, this whole loop keeps on going round and round, and that way we have very minimal maintenance and very less human intervention. So let's go through the example of how we are scaling it, because we talked about K time series matrix and how do you handle them. So over here, we are using Spark to do the distributed processing. So let's take an example of those K training data. In this case, we have matrix 1 and matrix 2, and all the historical data and the observed values, which are pre-processed in the way that in a single row and specific run date. Now we are using Spark's UDF, which is user-defined functions, where we put all the Luminaire open source functions within this UDF and do the training process. So each of this metric will then generate a model object associated to that metric. And we store this model object. Now comes the scoring part. During the scoring part, we again pull the newer data points that needs to be scored. So in this case, you see the time series column has 4.1 and 4.2 with some newer data points that needs to be scored. We pull the relevant model object that was stored in our database for those specific metrics. And then again, for the scoring, we again do a UDF using our open source functions to score. And the scoring then generates the scoring results for each of this matrix for each of the data points that were observed. And then you can use the scoring results to do all your downstream processes. So this kind of completely explains how we are leveraging Spark and building an AutoML process. So let's talk about other things that we added in our system and something that our listeners can also do, which is integrating with the central data systems. So we have our central systems that we wanted to make sure we have a centralized place for all this information about the data and the matrix and the health of the data. So, and one of the things was creating a self-service UI because we wanted to make it easier for anyone within our organization to create a data quality job. So it's just one click and one form for them to fill up, and we do all the orchestration behind it. As I said, we want to surface all of our health metrics related to the scoring on our central UI and tie that to the table which the monitoring was associated with to bring more transparency. We want to tag all the producers and consumers of that specific data to understand, to give us a clear picture, and if there are any anomalies, who needs to be notified. The one of this very important feature is the smart alerting, because alerting is setting up the thresholds for your alerting is always tricky. So what happens is our users always find it trickier to set up, like, should it be like if the anomaly probability is greater than 95%, should be greater than 98%, or anything, then I should be alerted. So what we have done is we are also abstracting that process away from them, and we are using data-driven decisions to figure out the sensitivity for them. This helps us to reduce some work for them and not sending too many wrong alerts. So let's go to some of the future directions for our system as well as our open source package. As we talked about, that currently our open source package only supports time series, but we want to go beyond that as well. So we will be working more on that. And also we will be happy to take more contributions as well from the community. We want to build decision systems for not just the data, but also for our ML pipelines. As I said, we want to also make sure the ML or AI pipelines, and we want to monitor their performances as well. Now, what we were talked about was only doing detection, but we also want to do and go another step ahead by diagnosing the problems and figuring out the fix. So that's what we want to incorporate, is the root cause analysis. And at the end, as Sayan mentioned, like some of the problems or the anomalies that happens, user might have more feedback or understanding on why this is an anomaly. So we want to also incorporate user feedback to get those labeled information. So let me wrap it up about all the talk that we did so far. So we talked about Luminaire as our platform, and also Luminaire as our Python library, which we have open sourced, which supports anomaly detection for a wide variety of time series patterns and use cases. We also talked about a proposed technique to build a fully automated anomaly detection system that scales for big data use cases and also require very minimal maintenance. Thank you everyone for attending our presentation. We'll go over through our questions right now. And just wanted to let everyone know Zillow is growing and doing a lot of hiring right now. And we also have some open positions in our team. And if you're interested in this type of work, I encourage you to apply or reach out to us on LinkedIn. Thank you very much.